Hello, I'm glad to see you again. And let's start our lecture number 2 on avionics engineer. Okay, so today our topics is displays and man-machine interaction. The cockpit display system provides a visual presentation of the information and data from the aircraft sensors and systems to the pilot, and certainly crew, to enable the pilot to fly the aircraft safely and carry out the mission. They are thus vital to the operation of any aircraft as they provide the pilot, whether civil or military, with primarily flight information, navigation information, engine data, airframe data, and warning information. The military pilot has also a wide array of additional information to view, such as infrared imaging sensors, radar, tactical mission data, weapon aiming, threat warning. The pilot is able to rapidly absorb the process substantial amounts of visual information. But it is clear that the information must be displayed in a way which can be readily assimilated, and unnecessary information must be eliminated to ease the pilot task in high workload situations. I hope you agree with me in this case, right? A number of developments have taken place to improve the pilot display interaction, and this is a continuing activity as new technology and components become available. Examples of these developments are head-up displays, helmet mounting displays, multifunction color displays, digitally generated color moving map displays, synthetic pictorial imagery, displays management using intelligent knowledge-based system technology, improved understanding of human factors, and involvement of human factor specialists from the initial cockpit design stage. Equally important and complementary to the cockpit display system in the man-machine interaction are the means provided for the pilot to control the operation of the avionics system and to enter data. Again, this is a field where continual development is taking place. Multifunctional keyboards and multifunctional touch panel displays are now widely used. Speech recognition technology has now reached sufficient maturity for direct voice input control to be installed in the new generation of military aircraft. Audio warning systems are now well established in both military and civil aircraft. The integration and management of all the display surfaces by audio inputs enables a very significant reduction in the pilot's workload to be achieved in the new generation of single-seat fighter or strike aircraft. Other methods of data entry which are being evaluated include the use of eye tracker. Next subtopic today's lecture is head-up display. Head-up displays, HUD. Without doubt, the most important advance to data is the visual presentation of data to the pilot, and has been introduction and progressive development of the head-up display, or simply HUD. The first production HUDs, in fact, went into service in 1962 in the Buccaneer strike aircraft in the UK. The HUD has enabled a major improvement in man-machine interaction to be achieved, as the pilot is able to view and assimilate the essential flight data generated by sensors and systems in the aircraft, while held up and maintain full visual concentration on the outside port scene. A head-up display basically projects a collimated display in the pilot's head-up forward line of sight, so that he can view both the display information and the outside board scene at the same time. The fundamental importance of collimating the display cannot be overemphasized and will be explained in more detail a bit later. Because the display is collimated, that is focused at infinity or a long distance ahead. The pilot's gaze angle of the display symbology does not change with head movement, so that the overlaid symbology remains conformal or established with the outside port scene. The pilot is thus able to absorb both distant outside board and objects and display data at the same time, without having to change the direction of gaze or refocus the eye. There are no parallax errors and aiming symbols for either a flight path direction or for weapon aiming in the case of a combat aircraft, remaining overlaid on a distant target, irrespective of the pilot's head movement. Right, sightseeing on a landmark using a mark on a window. The aiming mark moves off the target if the head is moved sideways. This effect is called parallax. The advantages of head-up presentation of essential flight data, such as the artificial horizon, pitch angle, bank angle, flight path vector, FI, airspeed, and heading, can be seen in this slide, which shows a typical head-up display as viewed by the pilot during the landing phase. The pilot is thus free to concentrate on the outside board during maneuvers and does not need to look down at the cockpit instrument or head-down display. It should be noted that there is a transition time of 1 second or more to refocus the eyes from viewing distant objects to viewing near objects a meter or less away, such as the cockpit instruments and displays and adapt to the cockpit flight environment. In combat situations, it is essential for survival that the pilot is head up and scanning for possible threats from any direction. The very high accuracy, which can be achieved by a HUD and computerized weapon aiming system together, with the ability to remain head up in combat, have made the HUD an essential system on all modern combat aircraft. They have also been widely retrofitted to earlier generation fighters and strike aircraft as part of a cost-effective avionics systems update. This slide illustrates a typical weapon aiming display. By using a forward-looking infrared sensor, FLIR, an electro-optical image of the scene in front of the aircraft can be overlaid on the real port scene with a raster mode HUD. The TV raster picture generated from the FLIR sensor video is projected on the HUD and scaled 1:1 with the outside board, enabling the pilot to fly at low level by night in fair weather. This provides a realistic night attack capability to relatively simple day ground attack fighter. HUDs are now being installed in civil aircraft for reasons such as inherent advantages of head-up presentation of primary flight information, including depiction of the aircraft's flight path vector, resulting in improved situational awareness and increased safety in circumstances such as wind shear or terrain avoidance maneuver. Or to avoid automatic landing guidance to enable the pilot to land the aircraft safely in conditions of very low visibility due to fog as a backup and monitor for the automatic landing system. The display of taxiway guidance is also being considered. Or enhanced vision using a raster mode HUD to project a clear video picture of the outside world from the FLIR sensor installed in the aircraft, or a synthetic picture of the outside world generated from a forward-looking millimetric radar sensor in the aircraft. These enhanced vision systems are being actively developed and will enable the pilot to land the aircraft in conditions of very low or even zero visibility at airfields, not equipped with adequate all-weather guidance systems such as ILS or MLS. The basic configurations of HUD is shown schematically in next slide. The pilot views the outside world through the HUD combiner glass and windscreen. The combiner glass is actively a see-through mirror with a high optical transmission efficiency, so that there is a little loss of visibility looking through the combiner and windscreen. It is called a combiner as it optically combines the collimated display symbology with the outside world seen viewed through it. Referring to figure, the display symbology generated from the aircraft sensors and systems, such as the INS and air data, is displayed on the surface of cathode ray tube, CRT. The display images are then relayed through a relay lens system, which magnifies the display and corrects for some of the optical errors, which are otherwise present in the system. The related display images are then reflected through an angle of near 90 degrees by the fold mirror and thanks to the collimating lens, which collimates the display images, which are then reflected from the combiner glass into the pilot's forward view field of view. The virtual images of the display symbology appear to the pilot to be at infinity and overlay the distant board scene as they are collimated. The function of the fold mirror is to enable a compact optical configuration to be achieved so that the HUD occupies the minimum possible space in the cockpit. The fundamental importance of collimation to any HUD system merits further explanation for the benefit of readers or any other pilot who knowledge of optical needs refreshing. A collimator is defined as an optical system of finite focal length with an image source at the focal plane. Rays of light emanating from a particular point on the focal plane exit from the collimating system as a parallel bunch of rays, as if they came from a source at infinity. Figures A and B here on the slide show a simple collimated lens system with the rays traced from a source at the center O, and a point D on the focal plane respectively. A ray from a point on the focal plane, which goes through the center of the lens, is not refracted and is referred to as the non-deviated ray. The other rays emanating from the point are all parallel to the non-deviating ray after exiting the collimator. It should be noted that the collimated lens, in practice, would be made of several elements to minimize the unacceptable shortcoming of a single element. It can be seen from the figure A that an observer looking parallel to the optical axis will see point O at eye positions A, B, and C, and the angle of gaze to view O is independent of the displacement of the eye from the optical axis. Similarly, it can be seen from figure B that the angle of the gaze from the observer to see point D is the same for eye positions A, B, and C, and is independent of translation. The refractive HUD optical system, in fact, is basically similar to the simple optical collimation system shown in this figure. The rays are traced for the observer to see points D, O, and E on the display, with eye positions at points A, B, and C. It can be seen that the angles of gaze to see points D, O, and E are the same from points A, B, or C. Are you agree? Please check it out. Okay, let's continue. The appearance of the collimated display is thus independent of the position or translation of the eye and is only dependent on the angle of gaze. Also, because of collimation, the display appears to be at infinity as the rays emanating from any point on the display are all parallel after exiting the collimating system. It should be noted that the display images must be correctly collimated. Decollimation is the term used when the light from a given point on the display does not leave the optical system parallel over the entire lens surface. The light can converge, diverge, or otherwise misbehave, resulting in swimming of the display images when the pilot's head moves. Sometimes this creates discomfort, and in the case of convergence, can even cause nausea. A very important parameter with any HUD is the field of view, which should be as large as possible within the severe space constraints imposed to the cockpit geometry. So, field of view so often has an abbreviation as FOV. A large horizontal field of view is particularly important to enable the pilot to look into turn when the HUD forms part of a night vision system, and the only visibility the pilot has the outside world is the FLIR image displayed on the HUD. It is important to distinguish between the instantaneous field of view, IFOV, and the total field of view, TFOV, over HUD, as the two are not the same in the case of the refractive type of HUD. The instantaneous field of view is the angular coverage of the imagery which can be seen by the observer at any specific instant, and is shown in the simplified diagram in figure A. It is determined by the diameter of the collimating lens D and the distance L of the observer's eyes from the collimating lens. The total field of view is the total angular coverage of the CRT imagery, which can be seen by moving the observer's eye position around. TFOV is determined by the diameter of the display A, and effective focal length of the collimating lens F. Reducing the value of L increases the IFOV, as can be seen in figure B, which shows the observer's normal eye position through sufficiently close to the collimating lens for the IFOV to equal the TFOV. However, this is not practical with the conventional type of HUD using refractive optics. This is because the cockpit geometry constraints on the pilot's eye position, and the space constraints on the diameter of the collimating lens. The IFOV is generally only about 2/3 of the TFOV. It can be seen from figure C that by moving the head up or down or even side to side, the observer can see a different part of the TFOV. Also, the IFOV is unchanged. The effect is like looking through and around a porthole formed by the virtual image of the collimating lens, as can be seen in this figure. The diagram shows the IFOV seen by both eyes cross-hatched, the IFOV seen by the left and right eyes respectively, and the TFOV. The analogy can be made of viewing a football match through a north hole in the fence, and this FOV characteristic of a HUD is often referred to as the north pole effect. Okay? The constraints involved in the HUD design are briefly outlined a bit later. For a given TFOV, the major variables are the CRT display diameter and the effective focal length of the collimating lens system. For minimum physical size and weight, a small diameter CRT and short focal length are desired. These parameters are usually balanced against the need for a large diameter collimating lens to give the maximum IFOV and a large focal length, which allows maximum accuracy. The diameter of the collimating lens is generally limited to between 75 millimeters and 175 millimeters, or 3 inches and 7 inches approximately. By cockpit space constraints and practical considerations, large lenses are very heavy and liable to break under thermal shock. The HUD combiner occupies the prime cockpit location right in the center of the pilot's forward line of view and the top of the glare shield. The size of the combiner is determined by the desired FOV and the cockpit geometry, especially the pilot's seating position. The main body of the HUD, containing the optics and electronics, must be sunk down behind the instrument panel in order to give an unrestricted view down over the nose of the aircraft during the high altitude maneuver, as you can refer to in this slide. The pilot's design eye position for the HUD is determined by pilot comfort and the ability to view the cockpit instrument and head-down displays, and at the same time achieves the maximum outside board visibility. In the case of a combat aircraft, There is also the ejection line clearance to avoid the pilot being nicked by the HUD on eject, which further constrains the design eye position. Typical IFOVs range from about 13 degrees 20 to 18, with a corresponding TFOV of about 20 to 25 degrees. The total vertical FOV over HUD can be increased to around 18 degrees by the use of a dual combiner configuration, rather like a Venetian blind. Effectively, two overlapping portholes are provided, displayed vertically. The effect of the cockpit space and geometry constraints is that the HUD design has to be tailor-made for each aircraft type, and a standard HUD, which would be interchangeable across a range of different aircraft types, is not a practical proposition. The conventional combiner glass in a refractive HUD has multi-layer coating, which reflect a proportion of the collimated displayed imagery and transmit a large proportion of the outside form, so that the loss of visibility is fairly smooth. A pilot looking through the combiner of such a HUD sees the real world at 70% brightness, upon which it superimposed the collimated display at 30% of the CRT brightness, taking typical transmission and reflection efficiency. The situation is shown in this figure and is essentially a rather low system with 30% of the real world brightness thrown away, equivalent to wearing sunglasses, as is 70% of the CRT display's brightness. In order to achieve an adequate contrast ratio so that the display can be seen against the sky at high altitude or against sunlight clouds, it is necessary to achieve a display brightness of 30,000 scantel per square meter from the CRT. In fact, it is the brightness requirement, in particular, which eschews the use of the CRT as the display source for some considerable time to come, even with the much higher optical efficiencies, which can be achieved by exploding holographic optical elements. The use of holographically generated optical elements can enable the FOV to be increased by a factor of 2 or more, with the instantaneous FOV equal to the total FOV. Very much brighter displays together with a negligible loss in outside world visibility can also be achieved, as will be explained in the next section of our lecture. High optical transmission through the combiner is required so as not to degrade the acquisition of small targets at long distances. It should be noted, however, that the development of rugged dielectric coatings apply to the combiners of conventional refractive HUDs has enabled very bright displays with sky outside world transmission to be achieved, comparable in part with holographic HUDs. A root gate dielectric coating is a multi-layer coating having a sinusoidally varying refractive index with thickness, which can synthesize a very sharply defined narrow wavelength band reflecting coating, typically around 15 nanometer as the CRT phosphor peak emission. The coating exhibits similar high reflection and transmission values to holographic coating, but is not capable of generating optical power. The IFOV of a refractive HUD using a combined with a root K dielectric coating still suffer from the same limitation and cannot be increased like a holographic HUD. It can nevertheless provide a very competitive solution for application where a maximum IFOV of up to 20 degrees is acceptable. Our next topic of part of this lecture is holographic HUD. The requirement for a large FOV is driven by the use of the HUD to display a collimated TV picture of the FLIR sensor output to enable the pilot to see through the HUD FOV in conditions of poor visibility, particularly night operation. It should be noted that the FLIR sensor can also penetrate through the haze and many cloud conditions and provide enhanced vision as the FLIR display is accurately overlaid one-to-one with the real world. The need for a wide FOV when maneuvering at night at low level can be seen in this figure. The wider azimuth FOV is essential for the pilot to see into the turn. The analogy has been made of trying to drive a car around Hyde Park Corner with a shuttered or park windscreen, with your vision restricted to a hole punch through the window. In a modern wide FOV holographic HUD, the display collimation is carried out by the combiner, which is given optical power or curvature such that it performs the displayed image collimation. And this figure shows the basic configuration of a modern single combiner holographic HUD. The CRT display is focused by the relay lens system to form an intermediate image as the focus of the powered combiner. The intermediate image is then reflected from the fold mirror to the combiner. This acts as a collimator as the tuned holographic coating on the spherical surface of the combiner reflects the green light from the CRT display and forms a collimated display image as the pilot's designed high position. And this figure illustrates the collimating action of a spherical reflecting surface. The collimating action is in part the optical reciprocal of the Newton's reflecting telescope, because the collimating element is located in the combiner. The porthole is considerably nearer to the pilot than a comparable reflective HUD design. The collimating element can also be made much larger than the collimating lens of a refractive HUD within the same cockpit constraint. The IFOV can thus be increased by a factor of 2 or more, and the instantaneous and total FOVs are generally the same as the pilot is effectively inside the viewing porthole. This type of HUD is sometimes referred to as projected porthole HUD, and the image is what is known as pupil forming. The displayed imagery can, in fact, only be seen within the head motion box. If the eyes or head move outside a three-dimensional box set in space around the pilot's normal head position, then the display fades out. It literally becomes a case of now you see it and now you don't, as the head motion box leads. Modern holographic HUDs are designed to have a reasonably sized head motion box so that the pilot is not unduly constrained. This figure illustrates the head motion box concept. The combiner comprises a parallel plate sandwich of planar convex and planar concave glass plates with a holographic coating on the spherical interface between them. The holographic coating is formed on the spherical surface of the planar convex glass plate, and the concave surface glass forms a cover plate, so that the holographic coating can be hermetically sealed within the combiner. The holographic coating is sharply tuned so that it will reflect the green light of one particular wavelength from the CRT display with over 80% reflectivity, but transmit light at all other wavelengths with around 90% efficiency. The CRT phosphors generally used are P43 or P53 phosphors emitting green light with a predominant wavelength of around 540 nanometers, and the hologram is tuned to this wavelength. This gives extremely good transmission of the outside world through the combiner. The outside world view through the combiner appears very slightly pink as the green content of the outside world with a wavelength of around 540 nanometers is not transmitted through the combiner. The spherical reflecting surface of the combiner collimates the display imaginary, but there are large optical abbreviation errors introduced which must be corrected. These aberration errors are due to the large off-axis angle between the pilot's line of sight and the optical axis of the combiner, which results from the HUD configuration. Some correction can be made for these abbreviations by the relay lens system, but there is a practical limit to the amount of correction, which can be achieved with conventional optical elements without resorting to aspherical surfaces. This is where a unique property of holographically generated coating is used, namely the ability to introduce optical power within the coating so that it can correct the remaining abbreviation error. The powered holographic coating produces an effect equivalent to the local variations in the curvature of the spherical reflecting surface of combiner to correct the aberration error by diffracting the light at the appropriate point. The holographic coating is given optical power so that it behaves like a lens by using an auxiliary optical system to record a complex phase distribution on the combiner surface during the manufacturing process. This will be explained shortly. Holography was invented in 1947 by Dennis Garber, a Hungarian scientist working in the UK. Practical applications had to wait until the 1960s, when two American scientists, Emmett Lake and Joseph Apatican, used coherent light from the newly developed laser to record the first hologram. Holographic HUDs use reflection holograms, which depend for their operation on refractive index variations produced within a thin gelatin film sandwiched between two sheets of glass. This is really diffraction grating, and hence a more accurate name for such HUDs is destructive HUD. A holographic reflection coating is formed by exposing a thin film of photosensitive dichromated gelatin to two beams of coherent laser light. Due to the coherent nature of the accident, beams of series of interference fingers are formed throughout the depth of the gelatin film. During the developing process, these fringes are converted into planes of the high and low refractive index parallel to the film surface. To a first approximation, the refractive index change between adjacent planes in sinusoidal as opposed to the step function associated with multi-layer coating. During the developing process, the gelatin swells, producing an increase in the tuned wavelength. Retuning the hologram is achieved by baking the film, which reduces the thickness and hence the spacing between planes of constant refractive index. The designer, therefore, specifies a construction wavelength at a given angle of incidence after baking. This slide illustrates the planes or layers of varying refractive index formed in the holographic coating. The bandwidth of the angular reflection range is determined by the magnitude of the change in refractive index. This variable can be controlled during the developing process and is specified as the hologram modulation. At any point on the surface, the coating will only reflect a given wavelength of a small range of incidence angles. Outside this range of angles, the reflectivity drops off and very rapidly, and light of that wavelength will be transmitted through the coating. The effect is illustrated in these two figures. Rays 1 and 3 are insufficiently close to the reflection angle, theta, for them to be reflected, whereas ray 2 is incident at the design angle and is reflected. There is another more subtle feature of hologram, which gives particular advantages in all optical systems. That is the ability to change the tuned wavelength uniformly across the reflected surface. And this figure shows that the reflecting coating must be reflect the display wavelength at a different incident angle at the bottom of the combiner from that at the top. It is possible to achieve this effect with a hologram because it can be constructed from the design eye position. The process for producing the powered holographic combiner is very briefly outlined during our lecture. The process has three key stages: design and fabricate the computer-generated hologram, CGH, produce master hologram, and replicate copies for the holographic combiner element. The computer-generated hologram, or CGH, and construction optics create the complex wave front required to produce the master hologram. The computer-generated hologram, CGH, permits control of the power of the diffraction grating over the combiner, thus allowing correction of some level of optical distortion, resulting in a simplified relay length. The CGH design starts with the specification, performance, and detailed design of the relay length optic. This is used to define the combiner performance, and then that of the construction optics, which finally leads to the set of waves from polynomial defining the CGA. The whole process is iterative until a practical solution to all stages is achieved. The CGA is actually a diffraction grating etches into a chrome layer on a glass substrate by an electron beam. The master hologram is created using this complex wave front recorded onto a gelatin layer on a spherical glass substrate and is used as a template to produce the combiner element. The replication processes uses a scanning exposure technique where a laser beam is raster scanned across the replication substrate, which has been index made to the master substrate to produce a contact copy of the master hologram. It should be pointed out that the design of the holographic optical systems is a highly computer-intensive operation and would not be possible without a very extensive suite of optical design software. Development of the optical design software has required many years of effort, and holographic optical design is very much a task for the experts and professionals. A very close liaison with the holographic optical manufacturing team and facility is essential. And this figure is a graph of a next generation slide deck architecture combining holographic HUD with a powered holographic combiner. Next topic of lecture, HUD electronics. The basic functional elements of a modern HUD electronic system are shown in the next figure on this slide. These functional elements may be packaged so that the complete HUD system is contained in a simple unit, as in the Typhoon HUD above. The system may also be configured as two units, namely the display unit and electronics unit. The display unit contains the HUD optical assembly, CRT, display drive electronics, high and low voltage power supply. The electronic unit carried out the display processing, symbol generating, and interfacing to the aircraft system. The new generation of the aircraft with integrated modular avionics use standardized cards to carry out the HUD display processing and symbol generation tasks. These are housed in a rack in one of the environmentally controlled cabinets. The basic functional elements of the HUD electronics are described, will be described a bit briefly a bit later. The data bus interface decodes the serial digital data from the aircraft data bus, typically a MIL FTD 1553B data bus, to obtain the appropriate data from the aircraft subsystem and input this data to the display processor. The input data includes the primarily flight data from the air data system and the INS, such as height, airspeed, vertical speed, pitch, and bank angles, heading, flight path, velocity vector. Other data includes MLS or ILS, guidance signals, source management, and weapon aiming data. In the case of a combat aircraft, discrete signals such as command, warning, etc. The display processor processes this input data to derive the appropriate display format, carrying out tasks such as axis conversion, parameter conversion, and format management. In addition, the processor also controls the following functions, such as self-test, brightness control, especially important at low brightness level, mode sequences, calibration, and power supply control. The symbol generator carries out the display waveword generation task or digitally to enable the appropriate display symbology, like lines, circles, alphanumeric, and enough, to be through written on the HUD CRT. The symbols are made up of a straight line segment joining the appropriate points on the display surface in an analogous manner to adjoin the dots, child's picture book. Fixed symbols such as alphanumeric, crosses, circles, sized as required, are stored in the symbol-generated memory and called up as required. The necessary D to A conversions are carried out in the symbol generator, which outputs the appropriate analog and deflection voltage waveform and bright up waveform to control the display drive unit of the HUD CRT. The CRT beam is thus made to trace the outline of the line drawn symbol. The process be known as through or cursive writing. Low and fast cursive display writing systems are required for a day and night mode operation HUD. Daytime operation requires a slow cursive writing system to produce a sufficiently bright display, which can be viewed against a 30,000 candle per square meter. Or it's the same as 10,000 feet lumen, while a white cloud background. Nighttime operation requires identical appearance symbology to the daytime symbology to be overlaid on the raster TV clear picture displayed on the HUD. The appearance of raster-generated symbology can differ significantly from stroke written symbology, and pilots wish to see identical symbology night or day. A fast cursive display system is thus used in night mode operations, whereby the cursive symbology is drawn at high speed during the raster fly-back interval. The display is written at about 10 times and slow cursive speed, and this makes significant demand on the bandwidth and power requirements on the deflecting system. By taking a small number of lines on the top and bottom of the picture, typically around 20 lines total, the whole of the daytime symbology can be superimposed over the TV picture for night. Because of the higher reading speed, the brightness of the raster and fast cursive display was very initially only suitable for night or low ambient brightness use. However, improvements to CRTs, development of more efficient phosphor such as P53 and high-efficiency wavelength selective combiners have allowed raster and fast cursive brightness to be increased to around 3,000 candela per square meter, which is usable in daytime. The very wide range of ambient brightness levels, for which a day and night mode HUD must operate over, is worthy of note. CRT luminance levels range from 30,000 candela per square meter to 0.3 candela per square meter, a range of 10 in power 5/1. The display drive unit contains all the display drive electronics for the HUD CRT, including the high voltage and low voltage power supply unit. High linearity and high bandwidth X and Y deflection amplifiers are required to meet the HUD accuracy and cursive writing requirements. Video interface electronics are incorporated in the display drive electronics for the TV raster mode. Modern HUD systems are used as the prime display of primarily flight data such as height, airspeed, altitude, heating, and another. The HUD thus becomes a safety critical system when the pilot is flying head up at low altitude and relying on the HUD. Modern HUD systems for both military and civil aircraft are therefore being designed so that the probability of displaying hazardous or misleading information is of the order of less than 10 in power minus 9. The self-contained single unit HUD makes it an ideal system configuration for a safety critical HUD. Forward and backward path monitoring techniques can be employed to ensure that what is on display is what is actually commanded by the aircraft system. The monitoring features incorporated in the HUD electronics are shown in this slide. And from now, you are qualified enough to start work with your individual first assessment. Try to do it on time. If you met any difficulties, you may find me in my office for electronics. Okay? Success. Another subtopic today's lecture is civil aircraft HUD. This section explains their potential and importance in greater detail and covers the progress that has been made in producing visible systems for civil aircraft operations. The use of HUD by civil aviation operators is still a relatively novel practice, and it was estimated in 2009 that there were about 2,000 HUD installations in revenue service worldwide. This compares with over 15 million military HUD systems in service worldwide. The future built civil HUD systems look good, however, and the numbers are growing. The potential market over the next decade is estimated to be of the order of 5,000 systems. The main advantages of HUD in a civil aircraft are: first, increased safety by providing a better situational awareness for the pilot to control the aircraft by the head-up presentation of the primary flight information symbology, so that it is conformal with the outside port seat. The problems of severe wind shear conditions have been mentioned earlier in the introduction to this lecture. This slide shows how wind shear arises and problems it creates. Over 700 passengers were killed in the USS alone in accidents in recent years caused by wind shear. The HUD can also provide a flight path directed display, which allows for the effect of wind shear from the knowledge of the aircraft velocity vector, airspeed, height, and aerodynamic behavior. The HUD can also increase safety during terrain or traffic avoidance maneuvers. Ground proximity warning systems, GPWS, are a very valuable aid in avoiding terrain and enhanced GPWS, or ground proximity warning system, and will extend this protection still further. In circumstances, however, during a terrain escape maneuver, where the terrain is visible, the flight path vector, or FPV, displayed on the HUD provides an unambiguous presentation on whether or not the terrain will be missed. If the FPV is overlaid on terrain ahead, the aircraft will hit it, and in this situation, the crew must decide on another course of action as opposed to holding on to see what happens. Traffic collision avoidance systems, TCAS, provide traffic conflict, escape guidance, and are of great benefit in preventing mid-air collisions. Guidance, however, is provided head down, so the pilot is maneuvering on instruments while trying to acquire conflicting traffic visuals. The HUD enables the escape maneuver and search for traffic to be accomplished head-on. Safety improvements in the course of such speech states of a typical flight were predicted in a study published by Flight Safety Foundation. The study concluded that the HUD would likely have had a positive impact on the outcome of 30% of the fatal jet transport incidents documented over the period from 1958. Second, increased revenue earning ability by extended operation in lower weather minima. The HUD is used to monitor the automatic landing system and to enable the pilot to take over on aircraft, which are not equipped to full Category 3 automatic landing standard. Third, use of the HUD as part of an enhanced vision system to enable operations in lower weather minima at airfields not equipped with automatic landing aids, ILS or MLS. For example, the number of Type 2 and Type 3 ILS facilities in the US is very limited, typically less than 70. The revenue earning potential of enhanced vision systems is thus very considered. As explained a bit earlier, the HUD displays a video image of the real world ahead of the aircraft derived from a millimetric wavelength radar sensor and a FLIR sensor installed in the aircraft together with the overlaid primarily flight information and flight path parameters. And fourth, the use of the HUD for displaying ground taxiway guidance is being actively investigated and is considered a likely extension to the HUD's role. Ground taxiway guidance could be provided by differential GPS. Very often trials were carried out in the US by the FAA in 1992. The enhanced vision system used a millimetric wavelength radar operating at 35 GHz and 3 to 5 micron infrared imaging sensors. The infrared sensors provided useful imaging information in haze and high humidity conditions at a range which substantially exceeded at range of the pilot's eye. However, descending through typical cloud and fog conditions, the range was no better than could be seen by the eye. The 35 GHz radar sensor, however, was able to operate successfully under all weather conditions and enable a synthetic picture of the runway to be generated from the processed radar image at range from 2 to 2.5 miles. The pilots were able to identify the runway on which they intended to land at a range of about 1.7 miles. They were routinely able to fly to Category 3A minima from 50 feet decision height and 70 feet runway visual range using the HUD display of the radar-generated runway image and the overlaid primarily flight symbology as their sole means to conduct the published approach. The display of aircraft velocity vector on the HUD was found to be particularly helpful throughout the approach when used in conjunction with the electronic image of the outside board and enabled to control of the aircraft's flight path to be precisely matched. The evaluation pilots reported Cooper Harper ratings of 3, satisfactory without improvement, and with minimal compensation required to the pilot for desired performance. A 95 GHz radar was also evaluated with similar successful results. The resolution was better, however, than the 35 GHz radar due to the shorter wavelength. Active development of both radar and infrared enhanced vision sensor systems is continuing, and their introduction into civil operational service is anticipated in the next decade. This figure shows the effectiveness of an enhanced vision HUD display with overlaid primarily flight information symbology. An overhead-mounted HUD installation is practical in a civil aircraft, and its configuration generally adopted. Also, the glare shield HUDs are practical. There is rarely space to retrofit such a system, and this figure shows a civil HUD installation. The HUD elements are precisely located in a rigid mounting tray, which provides the necessary mechanical stability, and the combiner can fold out of the way when not required. The field of view is 30 degrees by 25 degrees. The optical configuration of the HUD is shown in this figure. The thin spherical combiner incorporates a rugged dielectric coating referred to earlier. These highly efficient selective wavelength coatings are very hard and are not affected by the atmosphere and permit to relatively thin combiner to be released, rather than to the thick sandwich necessary with combiners, exploding biologically based hologram. The mass of the combiner is greatly reduced, which in turn reduces the mechanical structure required to support it with sufficient rigidity, both in normal operation and in avoiding head injury during the crash conditions. It should be noted that the thin spherical combiner does not introduce any optical distortion of the outside bore. As I mentioned earlier, the transmission and reflectivity values of a rugged coating are comparable with holographic coating. The off-axis angle of the combiner is around 17 degrees and is considerably smaller with the overhead installation than it is with a military coating, which is typically around 30 degrees. The off-axis errors can be corrected with a conventional relay lens tray, and the optical power which can be provided by a holographic coating is not required. The HUD incorporates electronics which monitor performance, both forward and reverse paths, such as the integrity of the system, defined in terms of displaying hazardously misleading information to the pilot, equals that of the conventional head-down displays at a value of 10 in power minus 9. Blind landing guidance can be derived from the ILS system and enhanced by mixing positional information derived from the global positioning system data using appropriate algorithms. This guidance information can be drawn cursively on the HUD together with primarily flight information using suitable symbology. Such a system is known as a synthetic vision, as distinct from the enhanced vision. The latter system uses radar or infrared scanning systems, as described, and the imagery is raster drawn with stroke-written symbology overlay. Completely blind landing can be performed with a HUD system displaying synthetic vision guidance either, and primarily flight information, given that the required integrity is provided. This can be achieved by the addition of a second means of monitoring, which can be either a second HUD channel, or more realistically, the additional of a failed passive photofile. A combination of the HUD and the failed passive photofilers provides a cost-effective solution for extending the poor visibility operation of many air transport category aircraft. Next lecture, we will be devoting for helmet mounting display. And for now, I hope you enjoyed this lecture, and I'm looking forward to see you next time. Bye.